Welcome to homework.
Okay, so we know the initial decay rate, which is A0 here, can be equal to lambda n0, which is equal to natural log 2 over t 1/2 times n0. If we do some arrangement here, we have n0 is equal to A0 times t 1/2 over natural log 2. n0 is the number of nucleus that is represents or present in this question. And we know t 1/2 here is the half-life for the baryon. So we also know that the number of nucleus can be equal to spill mass over the molar mass of the baryon times Avogadro's number. So if we do some arrangement here, eventually we have the spill mass is equal to A0 T1/2 capital M over NA times natural log 2. So we know the initial decay rate is given as 500 microcuries, which is 5 times 10 to the power negative 4 curies. If we do some arrangement here, eventually we can convert it to decays per second, which is 1.85 times 10 to the power 7 decays per second. And we know the half-life of the baryon is given as 12 days, which is 1.0368 times 10 to the power 6 seconds. Since we know in 1 day there are 24 hours, and in 1 hour there are 3600 seconds. And we know the molar mass for the baryon is given as 131 gram per mole. And the Avogadro's number is 6.02 times 10 to the power 23 per mole. So now we can plug in the values back into the equation to determine the spill mass. So eventually we'll have the spill mass is equal to 6 times 10 to the power negative 9 grams, which is 6.0 nanograms. So now let's take a look at the second question. It was asking us how long should the lab be closed? Well, we know the decay rates with respect to the time can be equal to lambda n0e to the power of negative lambda t, which is equal to a0 times e to the power of negative lambda t. If we do some arrangement here, we have time t is equal to natural log RT over A0 divided by negative lambda. And we know the lambda is the decay constant, which is equal to A0 over N0. And from the previous calculation, we know N0 is equal to lowercase m over capital M times NA. So therefore, we have A0 over N0 is equal to A0 over lowercase m over capital M times NA, which will give us the decay constant is equal to A0 times capital M over lowercase m times NA. So now we can do some rearrange. We can rearrange the equations for the time, which eventually give us the time t is equal to natural log RT over A0 times mNA, and then divided by negative capital M A0. So we know the final decay rates, or the decay rate we want is 1 microcuries. And the initial decay rate is 500 microcuries, which is 1.85 times 10 to the power 7 decays per second. And then we know the spill mass is 6 times 10 to the power negative 9 grams. Avogadro's number is 6.02 times 10 to the power 23 per mole. And the molar mass is 131 gram per mole. So now we can plug in these values back into the equation to determine the time. As you can tell, I use two different forms for the initial decay rates. So in the natural log, I use 500 microcuries, but under the denominator, I use the 1.85 times 10 to the power 7 decays per second. It's because our goal is to determine the time, and we know the SI unit for the time is second. So that's why I use two different forms here. It will be so much easier if you just leave the initial decay rates in microcuries, since we know the goal or the final decay rates we're looking for is 1 microcuries. As you can tell, these two units can be canceled out eventually. So I think it's much easier if you can leave it like this. But since our final goal based on this calculation is to determine the time. So therefore, that's why I convert it to 1.85 times 10 to the power 7 decays per second. So this calculation will eventually give us the time is equal to 9.26 times 10 to the power 6 second. If we convert to day, it's about 107.2 days, since we know in 1 day there are 24 hours, and in 1 hour there are 3600 seconds. So since now we got the time in days is 107.2 days, we need to run it down to 108 days because I'm a health physicist. I want to make sure the lab is completely safe. If I run it down to 107, I know it's not completely safe because the decay rates will be still above 1 microcuries. So safety-wise, I have to give the lab an extra more than half a day, maybe even extra day to make sure the lab's completely safe. So that's why I round that to 100 days. So the answer here should be 100 days. So the lab should close 108 days. Okay. And these are the answers for this question.